Now let me introduce some notation. Suppose R plus dot is a ring and take an element A in R. Suppose I take non-zero element, so A in R star. Then for n in n by a to the power n, we mean by a to the power n, we mean, so what is a to the power n? A to the power n means a into a into a, how many times? N times. If R has identity, which we usually denote as 1, then we can also define a to the power 0 to be 1. So if there is identity, then by a to the power 0 we mean 1. We cannot write negative powers because we don't know whether the inverse of this element exists or not. So if the inverse of this element is exists, then we can talk about a to the power minus 1 or a to the power some integer, that is negative integer. Positive integer is always defined. Now similarly, by na we mean the sum of a n times. So if n is, n belongs to n. For 0, we know 0 times a means 0. So 0 a means 0 into a, you can say. So it is 0. And for negative integer, n, we mean na to be minus a plus minus a plus minus a, how many times? N is a negative integer, so it is mod n times. Means if you are taking minus 2a, then it simply means that minus a plus minus a 2 times. So this is the notation which we will use frequently, so it is necessary to introduce. Now let us do some observations. Observation. Suppose I take n to be a natural number and AB are the two non-zero elements of the ring. Then, as we have defined, Na we mean a plus a, how many times? N times. Now, let me multiply by b to this Na. So what will happen is that a plus a n times, and I am going to multiply b here, this is n times. By the distributed law of the ring, this can be written as a into b plus a into b. So this can be written as n times AB by definition of NA. Now also if you see this and take A common from this element, so by the law of distributivity it can also be written as A B plus B plus B n times. So this can be written as A dot NB. So what we have shown is that NA into B is same thing as N times A into B is same thing as A times N into B. So these three things are same. Now one more observation let us do. Suppose I take two elements M1, M2 in N, that is natural number, and I take two element AB in the ring take two non-zero element in the ring R. So now consider M1, M2, AB. So this situation. Now by above property, the product of these two is also integer, positive integer. This is an element of the ring A dot B you can say, and this is some integer outside. So we can by this observation write it as M1, M2, A into B. We can write it like this. So as soon as you will talk about M2B, so this is M1 and this is M2B, M2A. So M2A is an element of the ring, and then M1 is an integer. So now again apply this formula. This is n times A, so this M1 times something into B. So we can write it as M1 M2A dot B. So we can write it like this. Now by this we can write it as M2A into M1B. So it means we can distribute this M1, M2, and as we have done for M1 first and M2 second, and so in the same way we can also write it as M1A, M2B. There is not any difference, because M1 in place of M1, M2 we can write M2, M1 and do the same process. So it will not affect the thing. So we can also write it like this. So suppose A is equal to B, then simply M1 M2 A square is same thing as M1A into M2A. We can write it like this. Now come to the observation number 3. Now suppose this is 3. Again take AB in R star, and suppose R is integral domain. So in place of any ring I take integral domain, and take some M in N such that m into a is equal to 0. Suppose it is happening in this integral domain. Then what will happen is that this implies ma into b is equal to 0 into b, that is 0, by the properties of ring. And now by this expression we can write it as a times mb is equal to 0. But we have taken integral domain and a and b are non-zero. Because a is non-zero, by the property of integral domain mb is equal to 0. So if I take a non-zero element a and a non-zero element b, and for some positive integer ma is 0, then mb will also be 0. And similarly, if mb will be 0, then a times mb will be 0. If a times mb will be 0, then ma into b will be 0. And now here, by the property of integral domain, b is non-zero, so ma has to be 0. So if for some integer ma is equal to 0, if and only if mb is equal to 0. Now what is ma? ma is a plus a m times. So it means ma is 0 means the order of a, that is additive order of a, will divide m. Okay, take it in another way. Suppose m is the smallest number for which ma is 0, then m will be the order of a. If m is the smallest number for which ma is 0, then m will also be the smallest number for which mb is 0. So it means the order of a is same thing as order of b. So what is conclusion here is that the order of any two non-zero element in an integral domain is same. So suppose AB is in R star and order of A is M, then order of B is also M, finite, and this is also finite, and is equal to the order of A. So order of any two non-zero element, so order of any two non-zero elements of the group, actually this order is, we are talking in this group, so additive order means, so order of any two non-zero elements of this is same mean equal. For finite case it is okay, they are equal. Suppose order of A is infinite and order of B is finite. If order of B is finite, then order of A will be finite. So if order of one element is finite, then order of all the elements are finite. It means order of one element is infinite, then order of all the elements, non-zero elements, are infinite. So we can say that the order of any two non-zero elements of the ring R plus is same. So it means order of a non-zero element of an integral domain, this is an integral domain actually, is somewhat special. So this number, if it is finite, is called the characteristic of the integral domain. So let me define it. Characteristic of an integral domain. Suppose R plus dot is an integral domain and for A in R star. So take a non-zero element, because the order mean additive order of any two non-zero elements are same. So if order of A means additive order of A is infinite, then we say characteristic of R is 0. So in place of infinitive we will say 0 characteristic. If order of A is equal to m, some finite number, then we say characteristic of R is m. We simply denote the characteristic as characteristic of R as characteristic of R. So this is a notation for characteristic to denote the characteristic of R. So for example, we have several examples. Suppose Z plus dot is a ring, then you know the additive order of any element is infinite, non-zero element is infinite. So this characteristic of Z is 0. Similarly, the characteristic of Q is 0. Similarly, the characteristic of R or characteristic of C is also 0. Now what about the characteristic of ZP? Now note one thing, that we have just defined the characteristic for an integral domain. We have not defined the characteristic for any general ring. And we know that if P is a prime, then ZP is an integral domain. Characteristic of ZP. So ZP is what? ZP with respect to addition is a cyclic group of order P, and the order of each non-identity element is P here. So the characteristic of this ring is P. What is characteristic of Z4? Note that this is not an integral domain, so we have not defined characteristic for this ring. Okay, so let us extend this definition and define the characteristic for any ring with identity. So characteristic of a ring with identity 1. Usually we denote identity by 1. So suppose R is a ring, so R plus dot is a ring with identity 1, then the additive order of 1 is called the characteristic of R, and it is denoted as characteristic of R. So we denote it like this. For example, now in case of Z4, how many elements are there? 0, 1, 2, 3. What is the order of 1? As a group with respect to addition, the order of 1 is 4, the order of 3 is 4, and the order of 2 is 2. So you can see that the order of each non-zero element is not same because it is not an integral domain. So order of 1 is 4, so we can say that the characteristic of Z4 is 4. Now I am going to give a criterion. So let me state a proposition. Characteristic of an integral domain is either 0 or a prime number. Let us prove it. The proof is very easy. As you can see, suppose R plus dot is an integral domain and its characteristic, okay, integral domain, if its characteristic, it's, so let me write like this, if characteristic of R is equal to 0, then there is nothing to do. Then there is nothing to do. Okay, because we have to prove that it is either 0 or prime. So if it is 0, then it's okay. If characteristic of R is equal to M, then we are to show. That M is a prime. M is a prime number. Okay, so we will show it. Suppose M is not a prime number, then what will happen? Suppose M is not a prime number. Suppose M is not a prime number. Then there exists M1, M2 such that, so this is a positive integer, so there exists M1, M2 in N, you can say such that M can be written as M1 into M2 and M1 is of course not equal to 1 because we are taking not a prime, so we need proper divisor M1, M2 and this is less than M. Suppose this is the situation. Now take A in R star, take a non-zero element R star, then M into A, that is MA. This can be written as M1, M2. Okay, so let us take A square here. So take A in R star because it is an integral domain, so a square will also be in r star, and now take a square here. So this is m1 m2 a square, and just now we have observed that this can be written as m1a and m2a. Now what is this? This is the characteristic. M is the characteristic, and characteristic is nothing but the additive order of every non-zero element. A is a non-zero element and this is also a non-zero element, so its order will be m. So m into a square is 0. Now we are in the situation that we are in integral domain, and in integral domain the product of two non-zero element cannot be 0. So product of two non-zero element is 0 means what? Or if you not take that these are non-zero, then product of two element is 0 means this implies that m1a is 0 or m2a is 0. But is it possible that m1a is 0? Because the additive order of a is m and m1 is less than m, so it cannot be 0. Now m2a is equal to 0, m2 is less than m, and additive order of a is m, so again this cannot be 0. So this is a contradiction, and this contradiction arises due to our assumption that m is not a prime, so it is wrong thing. So m is a prime number, hence m is a prime number. M is a prime number. So we have proved that characteristic of a ring of an integral domain is either 0 or it has to be a prime number. Okay, what is the meaning of this? Let us see. Suppose r plus dot is integral domain and characteristic of r is a p, where p is a prime number. So this is a prime number. Then in r plus, in this group, order of each non-zero element is p. Order of each non-zero element is p, where p is a prime. Okay. Now let us recall, if in a group G, order of each non-zero element is a power of prime, then that group is called P group. So I am taking prime to be P. So the order of each non-zero element is a power of prime P. Then that group is called P group. And there is one more result which follows from Lagrange's theorem and Silos's theorem simultaneously, that a finite, so let me recall, this is 1 and this was definition and this is a result. A finite group G is a P group if and only if order of G is equal to P to the power n for some n in n. So now what is the situation? Let us think over it. So this is a result from group theory, and it follows from Sylow's theorem and Lagrange's theorem also you have to apply. Both the theorem, if you will apply, then you will get this result. Not hard to say, it's proof. Okay, now apply it here in this setting. So what is our situation? R plus dot, this is the integral domain, and assume that the characteristic of R is P. Let us further assume that R is finite. So we have a finite integral domain of characteristic P. Then this implies that there exists n in n. Why? Because now R plus is a P group, because the order of each element is P. So R plus is a P group. Okay, let me write it also. R plus is a finite P group. Finite P group. Okay, so what does this implies? So finite P group mean there exists n in n such that, so this is such that order of R is equal to P to the power n. So this means order of any finite integral domain. You know what is finite integral domain? We have proved that finite integral domain is same thing as finite division ring, and which is same thing as finite field. These three terms are same. So once you have a finite integral domain and P is its characteristic, then the order of this set will be P to the power n. So this result can also be stated as if F is a finite field. Note one thing, that field is always a integral domain. So if F is a finite field, then finite field, so if it is integral domain, then it has also a characteristic, and characteristic of F is P, then order of F is equal to P to the power n, where n belongs to n. So the order of any finite field is P to the power n for some n. Okay. But one thing you should notice, that if you have a finite integral domain, then the characteristic of each element will be a prime number, and the order of whole integral domain will be P to the power some n. So one thing, let me write again. Characteristic of finite integral domain is always prime number. Always prime number mean always finite, and if it will be finite, it will be a prime number. So characteristic of a finite integral domain, that is the characteristic of a field, finite field, will always be a prime number. But it may happen that you have a infinite integral domain and its characteristic is prime. For example, suppose I take a polynomial ring over ZP X. So polynomial ring over ZP. In this polynomial ring, you can check this is a integral domain also, and the characteristic of this polynomial ring is P, because when you will sum one element P times, then the coefficient will become P times that coefficient. Let me come to the example. Suppose I take a polynomial a1x plus an x to the power n, and I sum it P times, that is multiplied by P, then what will happen is that PA0 plus PA1 plus PAN x to the power n, this is x we will get. But because these a0, a1, an are from ZP, so P times something will give you 0, so this is 0 plus 0x plus and so on, 0x to the power n, so it is a 0 polynomial. So this is infinite integral domain and its characteristic is finite. But if you have a finite integral domain, that will be a field and it will have a finite characteristic, because a finite group cannot have the element of infinite order. So it will have a finite characteristic. As soon as a finite characteristic, that characteristic will become a prime number. So it may happen that in finite integral domain in a finite integral domain you will have always a characteristic to be a finite prime number. But in case of infinite integral domain, the characteristic may be a prime number, and also just like in Z, the characteristic may be 0. This is also an infinite integral domain and its characteristic is 0. So it depends. Thank you. So let me make a correction while defining the characteristic of a ring with identity. So characteristic of a ring with identity is the additive order of the identity if its order is finite. If its order is finite, that is the order of multiplicative identity 1 is finite, then that number will be called as the characteristic of the ring. That is what we have defined previously, but there is one correction, that otherwise if this order is not finite, then the characteristic of the ring will be 0. For example, the characteristic of the ring Z4 is 4, because 1 plus 1 plus 1, the order of 1, this is 0 in Z4. So similarly, the characteristic of Z6 is 6. Similarly, if you see the characteristic of Zm, then it is M. Even if it is a prime number, then M is a prime number, then it will be P. So in general, the characteristic of any Zm, you can say its characteristic will be M. Now let us see the example of infinite characteristic. So as you can see that this is, let us see the example of a ring whose characteristic is 0. So as you can see that M n cross n Z is a ring with identity, but it is not an integral domain, and its identity is the identity matrix. So if you will go on adding identity matrix, you will never get the 0 matrix. So it means its order, that is the order of identity matrix in this ring is infinite, so its characteristic is 0. Similarly, if you see the matrix ring over Zm, so set of n cross n matrices over Zm, it also has the identity matrix, and when you will go on adding identity matrix, after adding m times you will get 0. So it means its characteristic is m. So it's okay. Please correct this mistake. Okay, thank you.